Hello, hello, welcome back to the lab, welcome back to EEforEveryone. In our last video, we were just talking about current sources, and we're going to be picking that up again today. We're going to be expanding on that fundamental principle of current regulation with a MOSFET and an op-amp by introducing a difference amplifier and an integrator into the mix. I'm very excited. I can't wait. Let's dive in. Yes, this is where we left off in our previous video. Remember this? Look familiar? Well, it's time to improve this design. Remember, there were some issues with steady state error. There were some issues with dynamic performance. And we're just going to, or transient performance, like when we do a input step response, there's some overshoot, there's some ringing. Perhaps we can improve the slew rate or make it a little more controllable. Right now, we're just kind of getting the gain, the intrinsic gain of the op-amp, and, well, maybe we want to limit that to something to control our slew rates. We don't really have that control right now, so let's add some of that control. Let's do it. I'm very excited. Okay, so fundamentally, we're going to be using two op-amp circuits. We're going to be using something called a difference amplifier, and we're going to be using something called an integrator. Let's start with the integrator. Difference amplifier? Leave a vote down in the no, I'm just kidding. We're gonna start with the difference amplifier. Okay. So this is fundamentally a op-amp. Hey, bet you'd never guess that. Got a positive and a negative input, just like any other. And what we're going to do is the positive input is configured like so. And the negative input is configured like so. This might look kind of familiar to someone who's built a non-inverting and an inverting op-amp before. It's kind of like the combination of the both. But here's what I like to do. For something like this, like a simple example, I tend to just use these with a gain of 1, where I just set all of these 4 resistors to the same value to make it have a gain of 1. However, you can modify these as a pair and these as a pair, keeping the ratio the same, to give it a simple gain of like 2 or 4, or there's an equation, you can look it up. But for today, we're just going to be using a gain of 1. Don't want to add too much complexity all at once. So when we're using this in our circuit, what we end up doing is we make this Vref, and then whenever our output is above the desired set point, we get a negative output here, or a positive output when it's the other way around. So basically we're saying there's a positive error, the output current, in this case, because we're regulating current, we're saying the output current is too low, I'm asking for more current, give me more, or we're saying the output is too high, give me less. Okay, so that's not the full picture. This is piece the first. This is basically our error amplifier. That's what we're using this as. We have an output that is proportional to the error from our set point to what we are seeing on the output. Okay, so this is basically our error amplifier. And what we're going to use to close the loop, so to speak, is an integrator. In this case, we're going to be using a non-inverting integrator. This is where it gets kind of weird. The reason why I wanted to do this separately, or second, is because this is where AC circuits kind of start to come into play. Basically what happens is the output of this op-amp is going to try to make this, I need to change colors. It's going to try to make this voltage equal to this voltage. And it's going to do that by trying to make a constant voltage appear at this node. But we've got a capacitor driving current through a resistor, which means that if we have a constant voltage on the input, let's say we have 1 volt on the input, that means the output is going to be changing at a certain rate, such that, says it's, what is it, I equals C dV dt? I equals C dV dt. That's a fundamental equation of a capacitor. Our capacitor is fixed. We're going to be driving a constant current through the capacitor by giving a constant rate of change on the voltage. That's pretty cool. That's the integrator. That's what it's doing. And so the reason why this is so cool is because if you pair our error signal, which is a constant proportional number representing the amount of error, for as long as that is positive, our integrator will keep ramping up the output voltage until the error goes away. And if our error is the other way, if the error is negative, it will keep turning down the output voltage until the error goes away. That's fundamentally how it works. And that makes it so, so cool because we can eliminate steady state error, because the only time the output of our integrator will stay constant is if the error term coming in is equal to 0. So if the current shunt is measuring exactly the voltage of our set point, the integrator will hold the MOSFET exactly where it is. That's the theory. So what we do is we take the output of our error amplifier, we feed it into the input of our integrator, we use the integrator to drive the MOSFET, and boom! We should have a current source that works incredibly well. At least that's the theory. Let's switch over to LTSpice and let's see how this works. Same story, different day. We're in LTSpice. We're ready to go. You can see that we still have our current shunt. We still have the pass element. We still have the same dynamic load. We got the same voltage input. But now we've got our op-amp integrator driving the gate, and we have this difference amplifier. Now, one thing that I want to make sure to call out here is there's something called an instrumentation amplifier that in some applications is necessary. You'll notice there's actually a load right here, and there's a load right here. So this 5K load is technically modulating our input a little bit. However, a 10 milliohm voltage source, that's a pretty stiff voltage source. I'm pretty sure that that 5K resistor is going to be inconsequential. But if this were more sensitive, what we could do is we could turn this into an instrumentation amplifier by adding a buffer. So you add a op-amp buffer to make a high impedance input to the difference amplifier, and that's where you get an instrumentation amplifier. So in this case, it's not necessary. We're not going to add the 2 extra op-amps. But if our voltage reference were not a stiff high impedance input, or a stiff low impedance input, or if we were measuring something that was a higher impedance rather than 10 milliohms, that could be required. So yeah, basically what we've got is we've got the same thing. We've got that input step response. Am I telling I have to go to a volt? No, we're good. We're good. Telling I have to go to 10 amps, just like last time. Okay, let's run the simulation. Let's see how it does. So our reference voltage step, ooh, you can see it's got a little more delay. That actually took quite a while to respond. You can see our input step happens, what are we at? That's at 1 second, as it should. But our current doesn't actually reach the set point till 0.06 seconds later. That's a lot slower, right? Remember when we were doing this step with the previous example with the gain of the op-amp directly driving this? It rode pretty close to that other wave. The shape was very similar. There's a little bit of overshoot, none of that here. But let's take a look at what is happening at the gate. Hey, look at that! When we give it the step input, when we give it the step input, you can see that there's this constant rate of change. That's the integrator doing its job. This constant rate of change on the gate until we reach our desired current, at which point the error term drops to 0 and we turn off. So the reason why there was so much delay is because there's this time right there where the gate voltage is increasing, but we haven't actually enhanced the MOSFET yet. That's what that is. We need to hit 3.6 volts before the MOSFET really does anything. Now there are other methods of compensating. We don't just need to use an integrator. Basically what we have right now is just an integrator. So if you're thinking about this like control theory, like PID, like control loops, proportional integrator derivative control, where you take those 3 and then you sum the combination and drive that to your MOSFET gate. This is just an integrator. Okay, this is a very simple controller, and we're going to make some iterative improvements in a future video, so make sure you subscribe so you don't miss it. It's going to be fun. We're going to be tuning this thing and improving the transient response. But for now, we should, because of this integrator, we should have completely eliminated that steady state error. Let's see how we did. Oh, now that is pretty good if I have ever seen it. 9.9985 amps. I'm going to do it. I'm going to calculate the percent error. So we got 10 minus 9.998557 divided by 10. That is 0.014% error. 0.014% error. I like it. Now, obviously, the real circuit would have more tolerance than that. Just our current shunt would probably be 1% tolerance part. But hey, that's pretty cool. It's never going to work better than the simulation. So it's awesome to see that it works well. Excellent. So yeah, how I feel about the step response is it's a little bit slower than I would like. I wish it would respond more accurate. Like if we were trying to do an impulse response with a very short duration, I don't know what kind of control you'd want to do, but if you were trying to do PWM control, this would definitely limit your PWM duty cycle because you need to wait for your regulator to get up to the set point. However, there's no overshoot, so if you're pretty sensitive to overshoot, that might be just fine. Right? Remember, this is regulating 200 volts on the input. 200 volts on the input is nothing to sneeze at. That is pretty darn good. Really just want to emphasize, we're going to be diving into PID control a little bit more. You might not be super familiar with the concept of integration, but if you're not, definitely hang around for the next one, where today we covered like that integrator behavior, but we're going to be covering the integrator, differentiator, and the proportional control blocks and how they get summed together to make the controller work, how to weigh those inputs, some things you might see in the transient response when one block is maybe weighed a little heavier than the other, some of the compromises you can make. So definitely check that out. We're going to be diving in more later. For now, let's just switch over our input to the dynamic input where we're going to be changing our current set point and look at how that impacts the system. Okay, I just want to speak to the elephant in the room. At least it's the elephant in the room for me. Some of you might hear the poor pupper in the other room. They're currently in heat, and for anyone who's been with a female dog in heat, they can be a little crazy sometimes, and that's pretty much how she responds to not being pet constantly. So, love her to death. She's absolutely fantastic, but you might hear her whining in the other room. Sorry about that. Anyways, we've got our voltage source swapped over, so let's zoom out here and give this a dynamic input. Hey, look at that! You can see that the integrator, I mean, it doesn't perfectly follow everything we're commanding. There's a little bit of phase delay. Maybe that corner doesn't look as snappy as I would like, but in general, right? In general, we're getting to where we should. Let's see if we get down to that 0.1 amp. Not quite. I mean, if we dwelled, we'd get down there eventually. It's just we're driving the integrator. So, yeah, you can see. It's just we turn around before the integrator gets there. It's approaching it. It's doing its dance. It's coming down. It's just we don't dwell because it's like a sharp corner. We didn't quite get there. But yeah, the integrator is doing its job. You can definitely see that up on the top part here. You can see that we get to, wait, that's voltage. Oh, that's the gate voltage. That's not what we want. We get to 24.999. That is pretty darn close to 25. That's 0.01 millivolts away. Again, incredibly low error, as it should be. And yeah, you notice when we're in that triangular region, we don't quite get to either one because the integrator doesn't have time to dwell to actually settle out and reach that zero error state. It takes a while to actually settle out to that zero error state. But we are still doing that phenomenal transient response where we're giving very sharp edges, but the current regulation remains. Again, very large amounts of power dissipated in that MOSFET. Again, not ideal as far as like an actual current source because of that. I really want to demonstrate how, with the PID, that basically there's limits here. Only having the integrator introduces some limits. And I want to expose that by increasing the slew rate by an order of magnitude. So these sharp transitions right here, these transitions are about to be 10 times steeper. And I just want to see how that impacts the regulation. Wow, that is really good. Okay, maybe we're going to go 2 orders of magnitude. This just almost feels unfair. That's just excessive. Okay, there we go. Now we're getting appreciable transients. And I just want to take a moment to acknowledge what this is, right? So what this is the error amplifier is saying, hey, there's error. But the integrator needs some time to move its bias point. It doesn't need to move much, but it needs to move. It needs to move in order to accommodate that change. And you can see here we were settled in at, what, 4.57. Oh, wow. That's actually a very small change. Oh, very small change. But that's where we're at. So we see these little glitches. And now, perhaps, if we added a D term, so the D term, fundamentally, it tells you the instantaneous rate of change. So it looks at the previous instant of time and this instant of time, and it tells you the difference, how much we jumped. Because, for example, with something like a MOSFET, we're at a certain bias point. And if we increase the voltage across that MOSFET a lot in one moment of time, what's going to happen is the current through it, it's basically a resistor, that current's going to shoot up. And that's what we see when this voltage drops. When this voltage drops, we see the current. Come on now. The current through it, when the voltage drops, the current through it spikes. And if we want to try to eliminate that, the D term can help to counter that by saying, hey, our current is going through the roof. Turn down that output voltage a lot. And then the integrator kind of, well, the D term is only there for a moment. During that transient, it goes away. The I term compensates for the steady state error again, and everything comes back to normal. But if we get our D term tuned just right, making this not just a simple I controller, might be able to improve the transient performance a lot, make it a lot more stable, help it to accommodate for things like this. Yeah, but we can't cover that all today, so you're definitely going to make sure to stay tuned for our next video. Yes, yes, yes. Coming up next, we are going to be improving the transient response by adding in the other elements of a control system, that is the P term and the D term. And we're going to be flipping this on its head rather than call it a current source. Let's say we call it a current sink, or perhaps one might say that's pretty close to an electronic load. Let's see how we might be able to flip this on its head and have a little bit of fun. Yes, indeed. I can't wait, and I hope you can't either. Okay, that's about all we've got for this video. If you liked it, don't forget to hit that like button, get subscribed, or consider checking out the links that we have in the description. A couple big ones, you will find this LTSpice simulation linked in the description. You will also find a link to our Patreon page. Thank you so much to those who have made this channel possible. I really appreciate you all chipping a buck in the hat. Love you guys. Yes, yes, most of all, I hope that you learned something great today. I hope that you enjoyed, and I hope to see you again soon. Thanks for watching. Thanks for staying till the end. Bye.